The research paper introduces a novel class of reverse map projection embeddings, inspired by cartographic projections. These embeddings address the drawback of amplitude embedding by preserving the norm of data. The authors show how these projections can be utilized as equivariant embeddings for quantum machine learning, leveraging symmetries in classical datasets to strengthen performance. The paper outlines the mathematical fundamentals, discusses well-known projections, and generalizes them to higher dimensions. It also describes how reverse map projections can be used as data embeddings for quantum computing and proves their equivariance with respect to unitary group representations. The authors compare the performance of 4 reverse map projections and amplitude embedding on a classification task, using both equivariant and non-equivariant models. The paper's structure includes sections on mathematical fundamentals, projections, reverse map projections, equivariance, and performance comparisons. The technical details and mathematical concepts are presented in a precise and professional manner, suitable for expert researchers and stakeholders. In this research, the authors introduce a novel framework for higher dimensional map projections, generalizing traditional map projections from R3 to higher dimensional spaces. They define a map projection as a projection from a point of projection onto a tangent hyperplane, allowing for the preservation of certain geometric features. The authors discuss 4 specific map projections: mnemonic, stereographic, twilight, and orthographic, highlighting their properties and uses. They also introduce a class of map projections, P-alpha, alpha element of -infinity, 1, which includes these 4 projections. This framework enables the study of map projections in higher dimensional spaces, opening up new avenues for research in cartography and geometry. The author's approach is rooted in Hilbert space theory and group representations, providing a solid mathematical foundation for their work. This research has significant implications for fields that rely on geometric transformations and projections, such as computer graphics, navigation, and data visualization. The research paper discusses the definition of a map P-alpha from the unit sphere SRn+1 to Rn+1, which is crucial for understanding various map projections, including mnemonic, stereographic, twilight, and orthographic. The map P-alpha is defined using a specific action, which depends on the parameter alpha. For alpha element of -infinity, 1, P-alpha is shown to be a bijection from a subset S-alpha of Srn+1 to Rn, with the codomain restricted to R-alpha. This bijection is vital for defining the embeddings E-alpha, which are used to create a connection between Rn and Rn+1. The paper also presents a detailed proof of the injectivity and surjectivity of P-alpha, R-alpha, S-alpha, ensuring that E-alpha is well defined. The definition of E-alpha is provided, showing that it maps points outside of R-alpha to points on the boundary of S-alpha, making it non-injective but suitable for quantum embedding purposes. The paper concludes by highlighting the importance of E-alpha for interactions with group representations in Section 5. Here is a combined summary of pages 7 and 8 of the research paper. The authors introduce a novel function, E-alpha, which maps a vector x in Rn to a quantum state in a Hilbert space H. The function E-alpha is defined as the point in S-alpha collinear with x, and 0, 0, alpha, where x is obtained by embedding x into the hyperplane of Rn+1 defined by xn equals 1. The authors prove that E-alpha, x, is a function of only parallel x parallel and alpha. The authors also explain how E-alpha can be used as a classic alto quantum data embedding. The state space of a quantum computer of n qubits is the complex Hilbert space H of dimension 2n. The set of possible quantum states on said quantum computer is given by Shish. The authors identify E-alpha with the composition of E-alpha and the canonical embedding R2n right-pointing arrow C2n. The authors then discuss group equivariance, a fundamental concept in quantum machine learning, QML. A function f v right-pointing arrow w is said to be equivariant with respect to a group G if for all G in G, we have that f, psi, G, v, equals phi, G, f, v, where psi and phi are representations of G on V and W, respectively. The authors prove that the property of equivariance is preserved under composition. In QML, Equivariant functions are crucial because they allow the incorporation of symmetry information about the data into the model structure, even before training. This can lead to dramatic increases in training accuracy and speed. The authors provide a simple method for determining whether a gate is equivariant and prove that the composition of finitely many equivariant functions is an equivariant function. Finally, the authors introduce a projection operator T-phi that maps an operator U in B, V, to an operator equivariant with respect to a finite group G. The operator T-phi is defined as the average of phi, G, U phi, G, asterisk operator over all G element of G. The authors prove that T-phi is a projection operator and that it maps an operator U to an equivariant operator. Here is a combined summary of pages 9 and 10. The authors establish the idempotence of T-phi, a crucial property allowing for the identification of unitary operators on a Hilbert space H that are equivariant with respect to a given group representation phi. This is achieved through the application of lemma 5.3 in direct calculations, demonstrating the linearity of T-phi. The authors then focus on the construction of equivariant embeddings, specifically the proof of theorem 5.5, which states that the direct sum ρ circled plus iota of a unitary representation ρ of a group G on Rn and the trivial representation iota is also a unitary representation of G on Rn plus 1. Furthermore, the embedding E alpha is shown to be equivariant with respect to G with representations ρ and ρ circled plus iota. The authors provide an intuitive understanding of theorem 5.5 by considering unitary operators on Hilbert spaces as generalized rotations and reflections. They then remark that the equivariance of E alpha is not disturbed when composing it with the natural embedding Rn plus 1 right pointing arrow Cn plus 1. The authors proceed to describe the experimental setup, where they investigate the performance of 4 different embeddings: reverse mnemonic, reverse stereographic, reverse twilight, and reverse orthographic, on a basic machine learning classification task using a quantum neural network, QNN. The data used consists of images of boots and sandals, with labels invariant to a Z2 symmetry. The authors leverage this symmetry to compare the performance of the embeddings in equivariant and non-equivariant setups. They also include standard amplitude embedding in their comparisons. The data is pre-processed by resizing images to 16 × 16 pixels and removing the final pixel, which is always black. In the equivariant case, the pixel is duplicated in its symmetric position to avoid serving as an indicator for the direction of the shoe. The research paper discusses the development of quantum neural networks, QNNs, with a focus on their equivariant properties. The authors introduce various embeddings, such as amplitude and reverse map projections, to classify data. They demonstrate the efficacy of their approach by comparing non-equivariant and equivariant QNNs on a classification task. The results show that the equivariant model outperforms the non-equivariant model in most cases, especially with the amplitude embedding. The study highlights the importance of equivariance in improving the performance of QNNs. Additionally, it raises questions about the optimal choice of reverse map projections and their resilience to noise in real-world applications. The authors suggest further investigation into these aspects to enhance the effectiveness of QML tasks. The research paper discusses the application of quantum neural networks, QNNs, for image classification tasks. It highlights the importance of equivariant QNNs, which maintain the symmetry of the input data, enhancing the model's performance. The authors utilize Qiskit for constructing and training the QNNs. They experiment with different equivariant and non-equivariant ansatz circuits, comparing their performance using cross-entropy loss. The results demonstrate the effectiveness of the equivariant approach, particularly with the reverse twilight mapping, achieving better training and testing times. The paper also emphasizes the importance of dataset size, suggesting that increasing it could further improve the model's accuracy. The summary covers key aspects of the paper, including the methodology, results, and implications, providing a clear and concise overview for expert audiences.